Estimating Friction Factors and K-Factors from Pressure Drop by Kirsten Phillips, Jordan Tice, Devin Wheeler, and Hannah Storr. The objectives for this experiment are to test for the total pressure drop across each system. From this, we can solve for the friction factors as well as solve for the K values on systems which contain the valve we're testing. Next, we want to make our own correlations between the friction factor and the Reynolds number. Next, for the design problem, we want to estimate the pump's power consumption. To do this, we must obtain all the information for our particular system, including the pipe lengths and fitting types. We want to use this information to calculate the total friction loss over the system to then solve for the total pressure drop. Then, the power consumption of the pump can be solved using the total friction loss, which was determined in the last step.
The first law of thermodynamics is the rate of energy accumulation in a system is equal to the flows of energy into the system minus the energy of flows out of the system. In this case, we begin with the following equation, where the change in energy is equal to the change in internal energy, potential energy, kinetic energy, and also includes enthalpy and workflows in and out of the system. In our case, the system has no accumulation of energy, and the energy balance can be simplified to a difference form, as seen here. The work of the system is the sum of the flow work and shaft work. Rearranging the energy balance and dividing by the flat mass flow rate, it now becomes the following equation. The flow work or pressure volume work is equivalent to pressure over density. The Q or heat term is combined with the change in internal energy and becomes the friction loss throughout the system. Finally, the equation becomes this final form as shown here. This equation is known as Bernoulli's equation. For our system, we could further simplify Bernoulli's equation. There is no shaft work, the system is horizontal, so there is no change in potential energy. Performing a material balance on the system, there is no mass accumulation, meaning mass in equals mass out. The diameter of the pipes is constant, and the fluid is assumed to be incompressible. Therefore, the change in kinetic energy is assumed to be negligible as well. The final equation becomes delta P over rho equals the loss in friction, where rho is the density of the fluid. In order to find the friction factor from our experimental data, we use the following equation, where delta x is the length of the pipe, v squared is the velocity of the fluid, and d is the diameter. The friction factor shown here is dimensionless and is called the fanning friction factor. Another common friction factor is the Darcy-Weisbach, which is 4 times the fanning friction factor. Most correlations are based on a Reynolds number, a dimensionless number calculated in the following equation, where d is the diameter, v is the velocity, rho is the density, and mu is the viscosity. For fittings and pipes such as valves, the following equation is used where K is defined as the velocity head. Now that we've learned a little bit about the experiment, it's time to head into lab.
To avoid performing in a dangerous lab, the following precautions should be administered. Wear personal protective equipment, or PPE, such as gloves, closed-toed shoes, and have your hair pulled back. For general lab safety etiquette, the following is relevant. In case of a fire, use CO2, dry chemical, or foam, because water may be inefficient. Also, in the event of a chemical spill, stop leakage and remove source of ignition and clean with an absorbent wipe. For safety in the lab during this experiment, a few things should be considered. Firstly, slips, trips, and falls. This point is mainly relevant because of possible water spills from the apparatus. Next is to stay aware. 2 other experiments are performed in the same lab at the same time. Because of this, all members must be aware of their surroundings to avoid mishaps. There is also the case of avoiding getting water and spills near electrical equipment such as the computer and probes. Finally, ergonomics is relevant because members must move pipes, check rates, and perform tasks that involve bending and standing for long periods of time. Also, keep a mop or material to clean up spills near the apparatus. In the case of chemical exposure in a respective area, rinse eyes with an eye wash bath, leave the room that is exposed to the chemical, or take off contaminated clothing and rinse skin in the safety shower.
Now that safety has been covered, it's time to begin the lab procedure. Start by turning on the computers on both sides of the equipment. While that's preparing, measure the temperature of the water in the tank. This should be done throughout the lab. All of the pipes that will be tested in the experiment should be placed and ready to be used to reduce transitional time losses. To switch out the pipes, 2 people will be needed. One person should unlatch the pipe and farthest from the valve and tip it to send any remaining water in the pipe back to the tank. With both ends unlatched, carefully take the pipe off the rack, being aware of other objects and people in the lab. Before starting the pump, ensure the pipes are tightly latched with the can locks on both ends and check that at least one valve is open at the end of the pipe to prevent restricted flow. Attach the 2 pressure transducer lines to the pipe. Now it's time to start the pump. Turn the frequency up slowly until the water is being pumped at a high flow rate. This will help remove air bubbles trapped in the pipe. To further remove bubbles, reverse the pressure transducer lines or choke the valve at the end of the pipe. Once the computer controls are on and ready, check and record the pressure differential reading for a possible offset. The system is now ready for data collection. On the input line in LabVIEW, enter the flow rate, motor frequency, and pipe description. Click record and stop after approximately 20 seconds. This will be done for a number of different pipes, with each being tested over different flow regimes. Additional data that is important to record in this lab is the length, diameter, and roughness of the pipes, along with the opening sizes of the valve. When it's time to test a valve on the pipe, the valve will need to be attached. The valve should also include 2 rubber gaskets and 2 metal latches. The rubber gaskets are placed between the pipe and the valve to create a seal, and the latches hold the pieces together.
We compared our data to several different correlations. For laminar flows in a pipe, the Hagen-Poiseuille equation is used to calculate friction factors, where the friction factor equals 16 divided by the Reynolds number. For turbulent flows in smooth pipes, the Blasius equation is used to calculate friction factors, where the friction factors equals the following equation, Re being the Reynolds number. For turbulent flows, the Colebrook-White equation can be used to calculate friction factors, where here epsilon is the relative roughness, d is the diameter, and Re is again the Reynolds number. For turbulent flows, the Moody correlation is typically used as part of a Moody chart, but can also be described by the following equation, where again the epsilon is relative roughness, d is diameter, and Re is the Reynolds number. For example, this is our data for a medium-sized steel pipe. Our data is the bottom line. One up is the Moody correlation, then the Colebrook-White, and finally the Blasius. The Moody correlation provides the best approximation of the set. The Blasius correlation is the least, and the Colebrook-White doesn't fit very well and must be solved iteratively, making it difficult. We recommend using the Moody equation to solve a network of similar pipes.
The design problem consists of 2 parts. The first is to find the total pressure drop from the outlet of the pump to the inlet of the pump across the system. The second part is to solve the power consumption of the pump. To solve for the pressure drop, information about the system must be compiled. First, we drew the system, taking note of different valve types and fittings within the system. Then, all pipe lengths and their heights were measured. To do this, we noted each pipe's material and their estimated diameter. For each pipe fitting, the average K values for each were found in Denevers and in Albright's Chemical Engineering Handbook. All valves were considered standard and full open. Elbows were considered standard and threaded. For the entrance effects, it was a flush entrance with sharp edges so that the R over D was equal to 0. The total friction loss of the system may be solved using the friction factor found earlier, the pipe diameter, pipe lengths, and the velocity of the specific trial. The friction loss in the pipes can be solved using the equation the total friction is equal to 4 times the friction factor multiplied by delta x over d times v squared over 2, where V is the velocity, delta X is the sum of all the pipe lengths in the system, and D is the diameter. The friction loss from the valves can be solved using the summation of the K values multiplied by V squared over 2. And because the velocity is constant throughout the system, the equation can be simplified to be V squared over 2 multiplied by the sum of all of the K values times the number of each fitting's occurrence in the system. The total friction factor is equal to the friction loss of the pipes plus the friction loss from the fittings. Once we have this, we can calculate the pressure drop across the system. To do this, we use Bernoulli's equation. After simplifying, we know that delta P is equal to negative times the density multiplied by the quantity of the total friction plus gravity times the change in height. Using the total friction loss solved to find the pressure drop, we can also find the power consumption of the pump. We know that the work of the system is equal to the PV workflow plus the shaft workflow. This is equal to the PV workflow on its own because the shaft work is negligible for this system. From the energy balance, we also know that the total friction loss is equal to the workflow of the system divided by the mass flow rate. Then we know that the hydraulic horsepower, or the HHP, which is the energy transferred to the water, equals the PV workflow, or the work of the system. The BHP, or the brake horsepower, which is the energy supplied to the pump by the motor, can be found using BHP equals the HHP divided by the efficiency of the pump. To retrieve the efficiency of the pump, it would require manufacturer information, and these are affected by many variables, for example, the material, the pump type, and the impeller diameter. To get an approximate value for this, the efficiency of the motor is instead used. Finally, the power consumption of the pump can be described by the equation. The BHP is equal to the PV workflow divided by the motor efficiency.
In conclusion, we found the friction factors, K values, pressure drop over the system, and we estimated the power consumption of the pump.